So, of course, the materials did not come into being in the way in which I'm presenting them. I reorganized the whole stuff to be able to go faster. Okay? So instead of doing it historical, it takes a long time, and I try to do it systematically. But actually, today we will come after 5 or 10 minutes to how the very first idea of an inconsistency adaptive logic originated. So, if you are still thinking in terms of the standard format with which I ended yesterday, remember this is defines an adaptive logic as a triple. So one of them is a lower limit logic, that's kind of the deductive part of the thing. And then you have a set of abnormalities, and the idea is that abnormalities are characterized by a logical form. And then, so you take it, the general idea behind the strategy is that you consider abnormalities as false as you can. Or put differently, that you take it that abnormalities are normally false. So you look for, in the case of inconsistency adaptive logics, as the abnormalities are contradictions, you take a as consistent as possible interpretation of the theory, in the sense that you take abnormalities that are not, contradictions that are not derivable from the theory by the lower limit logic, you take them to be false. That's the idea. But now it still has to be pushed into some form, into some practicable way. And the practicable way is that why does it? It goes back but not forward anymore. So I shall use. So the idea is that this triple. It's working. Thank you. Probably there's a bad influence of either my thumb or my brain on this thing. I hope it's my brain. So the idea is that the standard format defines your rules. And more precisely, the rules of deduction that we shall see come from two of the three elements, namely from the lower limit logic, that we find in terms of that two, from the lower limit logic and from the definition of the abnormalities. So in our case, very simple contradictions. So here are the rules. The first is a premise rule that is very simple. It says if something is a premise, you can write it down on the empty condition. You see there is a zero here. So if A is a premise, you can write down A at anywhere in the proof after any set of lines, even the empty set. You write down the premise and then the condition is zero. You have not to suppose anything in order to write down a premise. Okay, that's the idea. Premises are true, supposed to be true. Then there is an unconditional rule. That's the simpler one. And it says if you have some formulas on their condition, so that's to the right-hand side, the A1 to AN on conditions delta 1 to delta N. And if B is derivable by the lower limit logic from A1 to AN, then you can indeed add B and give it as the condition, the union of those deltas. Okay? So you need it in order to suppose, that's the idea, in order to suppose that the A's are true, you need it for each of the A's a certain condition. Now if something follows deductively, because that's the lower limit logic that you see there, if something follows deductively from those A's, namely B, follows deductively from the A's, then you simply can add B on the condition that stating that the conditions of the A's should all be possibly false. That's the idea. You can consider them in a systematic way to be false. I come back in a minute on that when I talk about strategies. And then there is the interesting rule that is specific for adaptive logics, because until now it just looks like you could do it just as well without conditions. But the interesting rule is the conditional one, because the conditional rule adds new conditions. Namely, what it says, if B or a certain disjunction of abnormalities, and this disjunction of contradictions, is LLL derivable from AN to A1, from A1 to AN, sorry. And to be LLL derivable, you can replace in this context by its derivable by your paraconsistent logic. I use a very simple paraconsistent logic in the examples that follow, but you can replace it by any other. Not the same things will follow, but the mechanism is exactly the same. I will say something about this adaptive logic in a second. So then, if from the A1 to AN, by the lower limit logic, here, sorry, wrong word. From the lower limit, by the lower limit logic, here paraconsistent logic, you can derive either B or this stands for a classical disjunction. So that means you need to have a classical disjunction somewhere in your language. Of course, you can always add one if you don't have one. Suppose that you have in the native language of the paraconsistent logic that you also have a defective disjunction. For example, a disjunction that allows for gaps or for bloods or for both. Then you, what is a disjunction gap, for example? It will be that you have reasons according to classical logic to take the disjunction to be true. For example, if you have P or Q, then if you have either P or Q, then normally by classical logic follows the disjunction of P and Q. But if you have a gap, that means that never, although P is Q or Q, sorry, P is true or Q is true, nevertheless the disjunction will not be true. Then that's a gap in the disjunction. Okay? A blood would be that neither P nor Q is true, but the disjunction is still true. So what you basically do is think about the simple and well-known rule, semantic convention in classical logic, and say, well, we have a different truth value either. I hope everybody got it. So what happens here now is that you still derive, if you have the A's on some condition, each of them, then you derive B on the union of those conditions, but now you add something, namely the members of delta should also be false. And I will give some examples that make this more intuitive in a second. Or maybe the subsequent example proofs will do the job.
There's a question over there.
Yeah, please.
Could you go back one slide?
Sure.
Just because maybe, I mean, I didn't catch it, sorry if I, yeah, about these rules, I just, I do catch like the premises of these rules are deductions, right? Are the derivations. So the premise of these rules is a derivation from A1 to AN and from delta 1 to
No,
delta.
no.
Or no, those are not derivations.
No. It's just like the rules in classical logic, like modus ponens, or is that form of rule, except that now the condition is sometimes added.
Okay, so these are just sequences of formulas, right? So these are sequences of, okay, that's just what I wanted, okay.
And another question is that the deltas there may be empty as well.
Yes, the deltas may all be empty. So as you will see in the example I shall present in a minute, where you start by writing down all the premises, all on the empty condition. And then you start from there. And the only rule that will introduce conditions is the conditional one. Okay? Please interrupt as much as possible. I told you yesterday I like that. Well, that's not a good reason to interrupt, but a good reason to interrupt is then I can react and make it clear, hopefully. Okay, so these are the rules. Of course, these rules are generic. Like in classical logic, you write down actually the rules like adjunction, simplification. These are generic rules. They operate in the meta language. Okay? Now, I hope that soon you will see. So, first of all, something about the logic that is used here. It's a logic that is called Clun. Oh, I don't need that. So the idea is simply that it is just like classical logic, except that it allows for gluts with respect to negation. It allows for some formulas A and not A to be true together. So then you have a negation glut. Because normally, if A is true, not A should be false, according to classical logic. So here you have a glut, because you have something that normally should be false, and that turns out to be true. So how is it defined? You take, first of all, full classical logic, the positive part of it, all the rules and so on of classical logic, but we're not considering rules for negation. You say all rules of like modus ponens, modus tollens, all that should be correct. Same for the quantifiers. And then you add, there are several possibilities, but one possibility is that you add A or not A. Or semantically, either A or not A should have the value 1. In other words, if A is false, then not A should be true, and vice versa. Okay, so if you look at the clause for negation in classical logic, this is something from my first paper on paraconsistent logic, which was published in 1980. So you have for negation in classical logic, you have two conditions. If A is, well, not A is, if A is false, then not A is true. And if A is true, not A is false. So the first requires completeness. One of them must be true. Okay? If one of them is false, the other must be true. The second requires consistency. They cannot be both true. If one is true, the other should be false. What happens here simply in Clun is that you forget about, well, you retain a completeness requirement. One of a formula and its negation is bound to be true, but you drop the consistency requirement. They can also be both true, and that's all. And of course, this gives you immediately a lot of changes. Think again about disjunctive syllogism, so where you have that A or B and not A, for example, then according to classical logic, I think everybody will be able to see it immediately. If both of these have to be true, And if, as is the case in classical logic, because of the consistency requirement, A and not A cannot be both true, then this A is bound to be false. And so in order for this disjunction to be true, B must be true. So in that case, B is derivable. B follows semantically. Okay? Now, as soon as you allow for inconsistencies, then you say, well, the fact that not A is true does not rule out that A is also true. Okay? You will give up consistency. But if A can be true, if there is a line in your truth table, if there is a possibility that A is true, then the disjunction of A and B is still true because of A, even if B is false. Okay? So in this case, B is not derivable anymore from these two premises. It's very simple. Okay? And that's exactly what happens in most paraconsistent logic. And this Clun logic is a kind of simplest, in a certain sense, paraconsistent logic. There is a student of Arnona from Idolav who has written an MA thesis in Tel Aviv to show that Clun is the intersection of paraconsistent logics that are not paracomplete, that do not allow for A and not A being both false. Okay, so they keep requiring one of them must be true, but that's all they require. I think we need this to understand a little bit in detail what we're doing. So, the adaptive logic I'm defining now or considering has Clun as its lower limit logic, so whatever follows by Clun follows unconditionally, is unavoidable as a deductive part. The abnormalities are simply contradictions, which then you can characterize in several ways, but one of them is the conjunction of A and not A is the set. Well, A and not A is an abnormality for every A that is a well-formed formula. And then there are several strategies. I come to that later. Here it doesn't matter which of the strategies you pick. The result will be pretty much the same. But I give you immediately an example where you see how the strategies lead to different choices and why. Okay. So I have this simplistic example there that I shall use to continue because I think it is a rather intuitive example. So what you see there is that you have P and Q and not Q, that are the premises, and not P or R and not Q or S. So according to a paraconsistent logic, no, I'll keep that for the next slide, sorry. I will not go on. This is a simple example proof where I start, as I said, by just writing down the premises, each of them on the empty condition. That's what the premise rule said on the previous slide. So I just write down the 5 premises. And of course, the lines are numbered, and you have the premises, then the rule by which they are written is prem, and the condition is empty. That's how simple. So now we can start the thing, and this is actually what led to the whole enterprise. This type of example. From 1 and 4, so from P and not P or R. You can, of course, derive P and not P or R. Okay? There is, and you can normally, in classical logic, you will do it in 2 steps, but it's obvious that it follows. Okay? So this followed by the unconditional rule. That means we just keep still the empty set here because both premises are introduced on an empty set. So deriving something from it by the lower limit logic still gives you the empty set. Should I use the mic? It's up to you to decide. And now we got to an interesting step that comes by the conditional. But I split it in very small steps on purpose to make it very simple. Since you have P and not P or Q, the OR is classical in Ghent. It's exactly the same disjunction as in classical logic. And so now you can apply this conditional rule by saying R is derivable from this, from formula 6, R is derivable on the condition that P and not P is false. If we can retain the hypothesis that P and not P is false, then R will follow. Remember, the idea is to localize inconsistencies at this point. So we have a theory that turned out to be inconsistent, and now we will see, we'll try to figure out what follows from this theory if inconsistencies are taken to be false, as many inconsistencies as possible are taken to be false. So if P is taken to be false, of course, then P and not P is taken to be false, then R will come out true. Can we take that to be false? Yeah, we can, as long as P and not P is not derivable by Ghent from the lower limit logic. And it is not. Okay, so then we try to do exactly the same thing with Q, and we find by precisely the same reasoning from premises 2 and 5, we are able to derive that S follows on the condition that Q and not Q can be considered to be false, can be taken to be false. Okay? So in that sense, they are completely parallel. But now there is of course a difference. That's why the example is made in this way. Namely, Q and not Q is of course derivable from the premises. From 2 and 3 follows immediately, premise 2 and premise 3 give you immediately the conjunction by Ghent because adjunction is perfectly retained in Ghent. So that's extremely simplistic. So that means what you see there now is that there is a mark or a check at line 8 because it says in view of what the situation of the proof at stage 9, after line 9 has been written, that's stage 9. So in principle, a proof starts off with nothing, and then you go to different stages. A stage is a sequence of lines, not a line. Okay, so the stage 1 will just have the first line, stage 2 will have the first and second line, and so on. Stage 9 will have the 9 lines you see on the blackboard now. And then you can consider that was a suggestion by Andrzej Wisniewski, can consider a proof as a sequence, or he used a chain of stages. Stage is a sequence of lines. Of course, you need precise definitions, but they exist and they are published, don't worry. Because the definitions are such, for example, that there is no need to retain the sequence of lines in the same order when you go to the next stage. The only point is that the same lines should still be there and then something new should be added. Okay. Now, good, what is the idea? Well, if you look at the premises, you see that it is unavoidable that Q and not Q are both true. So the conjunction is also true on the premises. So that means that S is not derivable from the premises if you minimize the inconsistencies. You want to interrupt?
No, sorry, I'm just trying to understand how you got 6 because I'm stupid.
No. How I got 6? Oh, well, you 6. Well, 6 you put together P and not P or R, and then if you put them together, there is.
But are there also parentheses or
Well, from A or B or C, you can derive that's even true in all relevant logics. A or B, sorry, this must be a conjunction. Wait a minute. Yeah, like this. So this is a valid rule in many logics for a start in classical logic, but also in all relevant logics, for example, Janssen and Balmer stuff. If you have A and a disjunction, then you either have A together with one disjunct or you have the other disjunct. Okay? Figure it out with the truth tables for yourself. It's extremely simple. Of course, this will not always hold in intuitionistic logic, but in material logic, let's say, it's bound to hold. And what I do there is I do not mention this step, I just go over it. Because my definitions of the rules were generic and said as long as it follows by the lower limit logic, you can apply it, okay? More here.
On line 6, could I have also defined a condition right there instead of 7, or it just happens on 7? Is there a restriction from where I assume my conditions?
No, well, to introduce this condition is a step. You need a rule to do it, and that's a conditional rule. And that's up to you. You decide where you apply the rule. It can be higher up or lower up. You can even, as I shall show in a minute on the blackboard, you can retain every condition empty until the very end of the thing, and then add a huge condition by just one application of the conditional rule. That's a very interesting question, yes.
maybe it would be simpler if the connection between 6 and 7 were made that 7 was derived from 6, right? So it's like 7 is purifying 6 by throwing the abnormality into the inside the set, right? But if you refer to 1 and 4 again, maybe that's the question. Why did 6, 7 in this order?
Well, either, of course, you can write 6 instead of 1 and 4
Yeah.
on line 7, that's absolutely correct.
Yeah.
But both are correct according to the conditional rule. And I think it is, since for the next line I do it differently, I take it at once for line 8, I derive the S from 2 and 5. Otherwise, I could also have derived a disjunction and then. But it's in order to suggest to the reader that these things are equivalent. Now you are actually pushing me to explain what I planned to explain on the blackboard, because I failed to add more. I could have added another slide in it, but I do it on the blackboard. Good. So it's okay?
No.
They solved it.
Yeah.
Ah, that's wrong. I should solve it. And then everybody would hear the solution. Good. But if you three are happy,
No, I was just asking what was the meaning of that 9 right over the end of
the
it.
check with the
Yeah,
9
the check and 9.
as a superscript. So that's from stage 9 on, this line is marked. So I gave you on the previous slide, I gave you the rules in a generic way, how you get to these generic rules from in terms of your lower limit logic and your set of abnormalities. But there is another aspect to understand the dynamics, namely that some lines are marked or unmarked. Well, lines are marked or unmarked. But that is not something you have to do. In the beginning was a mistake I made. I thought that you had to add a mark, that the person who wrote down the proof had to add the mark. And then some people, especially if a proof, we will see there are some complications with proofs that get only stable at an infinite point. So some people thought you actually require a transfinite number of steps. Actually, Ido thought so at a certain point. Because by accident I was able to visit Tel Aviv in the period that he was working with Armand. And so, but that's not the case, or I have reformulated the thing in such a way that you don't need that. So, the idea simply is, what it means is, from stage 9 on, line 8 will be marked. The idea is that if the formula derived at an unmarked line is supposed to be derivable from your premises. A formula derived at a marked line is supposed to be not derived in this way and not derivable in the way it is done there. So, in other words, you cannot derive S by relying on the consistency of P and not P. It's possible you can still derive S on a different way. There can be other premises that include R, for example. But so you should always be careful when a line is marked. It does not mean that the formula is not derivable. It just means this way of deriving it is not correct on the adaptive logic.
Thanks.
And this also has to do with the complexity of the thing. In sense, it simplifies. So, we'll try to. Now, this is an example that is related to inductive generalization. And this is a very simple and almost simplistic way of inductive generalization. Namely, this was presented, this is a part of what I presented in 2009, I guess in the very same room, but my memory is not good enough because I couldn't find the room, as you have seen, but I think we were sitting here. And the idea is you consider a set of data, and then there is a very simple, this is the simplest adaptive logic you can construct for inductive generalization, actually, namely, you take negations of generalizations to be abnormalities. So what you see there are abnormalities. It is not a case that all P are Q. That's supposed to be an abnormality. Okay, the normal situation is that all P's are Q or all P's are not Q, and things like that. Maybe I can at least at once add something to this, namely that I mentioned the upper limit logic yesterday. What you obtain if you say all abnormalities are false. The logic that you obtain. So that is, you say whenever there is an abnormality is true, you have triviality. That's the upper limit logic. Like for classical logic, for inconsistency adaptive logics, it's classical logic. It says as soon as there is an inconsistency somewhere, triviality follows. Okay? That's the real bad consequence that you get. Well, I think I'm going to open one of these to cool down my brain, which will make it easier to talk. Even the stick was suffering from it. So there is something special here, namely that it is not possible that all abnormalities are false. There's no model in which all abnormalities are false. I call it UCL logic, uniform classical logic. What the logic presupposes is that if there is something, this UCL logic, upper limit logic, what it presupposes is if there is an object that has certain properties, then all objects actually have those properties. You can also split it up a bit in smaller parts that give you an approximation to the idea, but not at once the full case. And you could say if some A are B, then all A are bound to be B. So how you express this semantically is by saying that the extension of a predicate is always either empty or universal. If the predicate is a relation for an n-ray relation, then all n-tuples will have the same extent, all n-tuples will either all be true or all false. Okay, the relevant n-tuples are. It's not clear because you frown, that's okay, I do not want to interfere with. Oh, I thought you were coming up with a question because you look at me like this is obscure. But no, don't worry.
Is the upper limit logic in this case
Is there?
propositional logic?
No, it does not make sense to do inductive generalization of a propositional line.
No, I mean because if every predicate is either true of all individuals or false of all individuals, it's just a proposition. It's true or false, a classical proposition.
No, but you need to say of all objects, okay? So the only way to define it is at the predicative level. It doesn't correspond. Well, you can officially you can construct the correspondence as saying a proposition of letter is simply a zero, a predicate of rank zero. Okay, that's always a trick you can always use. But it doesn't lead to anything. So this is even the upper limit logic, or that logic UCL is not true in is completely false in the world we live in. Okay, the world we live in is not possible according to UCL logic, because we know that there are diversities, fortunately. Suppose we all had the same properties, then it would be simple for people sitting in that committee to judge the talks, because you would say, well, everybody gets exactly the same quote. Okay? Because the four people talking yesterday would have been the same token. They all gave. So it's a logic you don't want to use for anything, except as a border case of the adaptive logic. Please, yes.
What are you showing with this proof here? So what is this proof showing?
What am I trying to, I still should start explaining what it shows. So I was talking about the idea of inductive generalization approached in this simplistic way. And simplistic ways, you have a set of data, and you try to figure out which generalizations can I derive from this data. Of course, derived does not mean derived deductively here. It's derived in a methodological way, as you can do. So derive, if you take it that abnormalities are as false as they can. given the premises. And that abnormality here is that there's an abnormality whenever generalization does not come out true. So actually it's slightly more complicated, but it's not worth to say much about it. Like P and Q should be, it only works for unary predicates, but that is well known. When in my youth I worked on Carnegie inductive logic, and Kemeny and Carnap have done a lot of work trying to get this inductive logic in terms of logical probabilities to apply that to relational predicates. Try to find an example for yourself tonight, and you will not be able to. So if you have relational predicates, so binary predicates for a start, then it's extremely difficult to make any sensible generalization in terms of that.
And so what's
Sure.
RD defined, or how's the RD defined to do RD? And in line 7, define RD, what's RD?
Oh, that's a derived rule. I'm sorry. I did not introduce that. I have to do it. Have to do it now. Let me check whether I have the right one in my head. What is going on here is that you consider two generalizations, all P are Q, and then later all P are not Q. And given the context from 3, you can derive A as property Q, and from 5.2, you can derive A does not have property Q. So if both generalizations would be true, a contradiction would follow. Then, as simply by classical logic, you can derive from that. So that means that either generalization, either the first generalization is false or the second is false. Because if both are true, then a contradiction follows, and that's not allowed in classical logic. That's not possible. Classical logic. Okay, that's all there is to this RD. But it is a very useful rule if you are looking for a proof or trying to show something. It's heuristically interesting. That's why it's worth mentioning it as a derived rule. And I think that's it. So what you see what happens here is that you cannot derive, in this case, actually any generalization. All you can derive is that some generalizations are incompatible with each other. Namely that if one of them, that either of them is bound to be false. That's what line 7 says.
I was trying to see exactly the steps you follow to prove. I think that you put from 6.1 and 6.3, you apply the rule of disjunction, right? You introduced earlier, but it seems like it's from 4.1, and I don't know exactly if I'm right, but I don't know if the numbers that in the steps are following the same structure that you put in the because I'm not finding the 6.1.
Maybe 1.6 must be 1.3. Prime is 4.1.
and maybe if for example, like I believe that the meaning of the step 7 is like it's not the case that for all x, if the x, then you have qx, or it's not the case for all x. If you have px, then you have not qx.
So it's not the case that all P are Q, and it's not the case that all P are not Q.
And some like I understand the structure, like for example, you found QA, and so if you find QA, then it's not the case that for all x, then px, if px, then not qx, okay. And as you found not q, it's not the case that QA, so and it's not the case that for all x, if px, then qx. But I don't know if I understand, like when you see the numbers in the steps, there's no 6.1, I believe that it's 4.1 and 6.3. And then the rule of
Yeah, here,
yeah,
this should be 4.1.
4.1.
Yes.
And if it is a brand,
Yeah, it's a typo. Not quite right. Over the years, the writing out proofs on slides is difficult, especially in things like LaTeX, and I ended up by trying to program it all in LaTeX definitions, so that I cannot make that mistake anymore. Just refer to some line, and then I will get the right number, like 4.1 instead of 6.1. But apparently in those days, when I wrote these slides for the first time, I was not there yet. Well, thanks, because it's always good to point out mistakes. Yeah.
Could you go back one slide? I'm trying to understand the role of the uppercase omega set. For example, when you conclude Q and not Q, are you adding this conjunction to the omega sets?
Sorry.
Like in the last line, when you get Q and not Q, does that mean you're adding this Q and not Q to the uppercase omega set, the set of anomalies?
No, it is Q and not Q is an abnormality. It's defined like that. It is and it always was. What you show here is that abnormality is actually derivable from the premises by the lower limit logic. So there's a distinction between what is an abnormality and is this abnormality derivable from the premises. Okay, that's all I'm saying at the moment. But does that help to solve your problem? Because the line 9 is simply from, well, look at line 2 and 3, it says Q, not Q, so this is simply addition for the unconditional rule. Addition, or sometimes called conjunction or adjunction. Sorry, not addition. Conjunction or adjunction. It's called. So what line 9 then causes line 8 to be marked, because the condition of line 8 cannot help to be false. It's derivable from the premises by the lower limit logic. Semantically, when we come there, you will see that it means there are no models in which Q are not, no models of the premises, no clone models of the premises in which Q and not Q is false. Is it okay or is it not completely clear? Then please go on and
I'm just wondering, what the set of abnormalities does.
The set of abnormalities is defined here. All formulas of the form A and not A, where A is a closed formula. W is a set of closed formulas. Otherwise, I use an F for closed and open formulas. Okay? Go back to the next slide. So this is better generalization. So this paper, a survey paper on all these things was written up after the 2009 conference here and was published by the organizers of the conference in, I think in Synthesa. Quite sure it was Synthesa, not Studia Lógica, but Synthesa. So that is available, and it's also available on my homepage in my bibliography. There was yesterday somebody asking about this paper showing that proofs give you new information. Did the email arrive?
Not as far as I saw, but I'm gonna double check now.
Because I send you the reference to my homepage and then say go to item page 18, you have item 4.55, and that's the paper. And the paper starts with the word blocks. Because it comes from considering chopping up formulas in blocks, into blocks.
Starts with the word block. I understand.
And then from there you will get a paper. If you press the off print, there is an off print reference. If you push that, if you click on it, you will see the paper in your browser, and from there you can download it very easily.
Okay, thank you.
I try to put as many papers in there, and that is actually because Logic puts everything open on the net after like 2 years or so as a policy. So there's no point in going open access anymore because it comes by itself, okay? And for free. But then I still put a copy on my website because the Logic Analyse website is at VUB and it doesn't work very well. Often you have to wait for like 2 hours before it finds a paper that you clicked on. And that's not very good. So if some people are interested in inductive generalization, I would suggest that they take a look at this paper written up after the conference for Newton da Costa in 2009, because I showed there that observations and experiments can be planned in this way, depending on the generalization logic you choose. You can figure out, given a certain situation, which is a sensible experiment to perform now, or which type of observations I should try to find, to do. Which I think at least tells us something about, well, the fact that scientists do not just do some things, but they can do some things in a purposeful way, even designing experiments or looking for certain observations rather than others. Please.
This is that the negations of negations are on so when defining the set of unknowns for first order, you you need to change the need to be done with the work.
This is just one of the possibilities. If you look at the paper, I remember that when I was giving the talk, Newton at some point looked as if he can't be serious. Now he still has all the more such logic. But for me, this is very important because I referred to it yesterday. Logicians are strange animals that if there is a problem and they find one solution, then they start crying, I got it, this is it, this is it. Instead of asking themselves, well, which variants are obviously possible? And then you have to choose, and then you see, for example, that there are like 12 logics, at least maybe 1200, I don't remember, that corresponds to the view of Popper on his deductivism. So Popper is extremely vague because he does not tell you exactly what to do. And so this is one kind of possibility, one kind of abnormalities that was there in the very first paper. But another kind of possibility is that you take as abnormalities a negative instance. So something like PA and all P are Q, PA and not, well, there is an X, would be maybe better. PX and not QX. And then you can even vary on these things. Because this is the way in which philosophers of science use negative instance. Logicians will say an instance of that thing is, there is an X, an instance, not a negative one, an instance is not PX or QX. And then the negation of this, if you then define in these terms a negative instance, you will come to the same thing, of course, but the idea of an instance is different. Yeah. Okay. But the point I'll try to make now is that there is content guidance in the sense that your specific theory tells you which is the kind of information you have to look for, not just from a logical point of view, but with respect to the domain you are working in and studying. Okay. Now about strategies, and I go back because I think it is simpler to give examples in terms of inconsistency adaptive logics, how you minimize inconsistencies. That's simpler than, for example, this inductive generalization. For one thing, inductive generalization always works at the predicative level. So I can explain strategies most easier. And I tell already what the problem is. We consider another premise set here. Sometimes you can, if you can derive an abnormality from the premises, as in this example, propositional example, then it is very simple. But very often you cannot derive an abnormality from the premises. You can derive only a disjunction of abnormalities. And then the point is, how will you handle this? And that's what strategies do. Some strategy will say, and that's the oldest one, well, if you have a disjunction of abnormalities, concern each of these, the disjuncts as unreliable. You cannot rely on those abnormalities in order to derive a formula. But there is an alternative that says, and that's really the idea of minimizing in the semantic sense, consider the minimally abnormal or minimally inconsistent models of premises. Then you go differently because it's possible that if you have a disjunction of, suppose that you have a disjunction A1 and A2 are both abnormalities. Sorry. Now it is possible that in the models in which A1 is true, you can derive P, and in the models in which A2 is true, you can also derive P. But there A1 will be false, so you have to derive P in a different way. But nevertheless, it's possible that in all minimally abnormal models you have the and this is supposed to be an example of that. And the premises, of course, they are made specifically to illustrate. You have P or Q, and then you see the next premises are not P or not Q. So that means P or Q is true, and then not P is also true, and not Q also. So if not Q is true, maybe I better go to the proof instead of trying to explain it in an abstract way. So what is obvious is that you can derive from the first three premises already that either P or not P or Q or, sorry, P and not P or Q and not Q, one of those two is bound to be true. And at the same time, you know that they are not both true, okay? So there will be models in which P and not P is true and Q and not Q is false if you apply minimal abnormality, and there will be other models in which is the other way around. But then if you look at, sorry, that's too fast. If you look at the other premises, it says if not P is true, well, either not P or R or not Q or S. So let us quickly look at oops. I think this is counterintuitive, that the button to go up, to go forward is the lower one, and the button to go upward is the upper one. At least this is counterintuitive to my mind.
Because you're in the southern hemisphere.
Everything. Okay. Good. Yeah, I got an email message somebody asking me at 9 o'clock yesterday morning whether I had had a good lunch. So I said, may I point out that we are in the southern hemisphere, and not only the hour is different, but also the seasons. So what you see is that you can indeed derive P and not P, or Q and not Q, but you cannot derive both. And in some cases, it's much more complicated. You have a whole set of abnormalities, maybe in the parallel, can be a lot, and you know that one of them is true, but you don't know which one. So then you have to take each possibility into account. And that's what the strategy will do. So this is the simpler strategy, namely the strategy that is called reliability. And that requires, sorry, I have to point out. This requires, whoops, I'm holding it upside down. That's so bad, sorry. So for the reliability strategy, you say some formulas are unreliable on gamma, on the premise set gamma. This means these are the abnormalities, contradictions in this case. I mentioned them here. So both of these are unreliable. And then on the other hand, minimal abnormality strategy requires a more complex definition in terms of, well, mathematically a little bit more complex in the sense that you need you take Sorry, I'm just not finding a term. There's something like A1 or A2 or A3. And then here you have more abnormalities, B1 or B2. And suppose that these are the disjunctions of abnormalities that you can derive in your proof. Then that minimal choice sets I was looking at. So what you do is you make a choice set, you say let's first pick A1 here and combine it with B2. And then we also pick A1 and combine it with B2, and then we do the same for the other A's. And then you consider the minimal choice sets, because it is possible that, for example, B2 is just A1. So if you then go for a minimal choice set, if you pick A1 here, you have to pick A1 here. Otherwise you get not a minimal choice. Okay? So I know mathematicians do not consider the case where the elements, the disjuncts may overlap. They do not consider that in the theory. But of course, I obviously need it because I have to define what should hold in a minimal abnormal model. That's the way to make the approach in terms of the syntax correspond to the semantics. I told you 2 days ago that we need new techniques to show such things. So this phi of gamma are the minimal choice sets of the disjunctions of abnormalities that you can derive.
The disjunction between abnormalities should be the classical one, right?
Yeah, it's the clone ones officially, that's the low limit logic, but they are exactly the same as the classical ones. So very often, for many paraconsistent logics actually, it holds that if classically you can show this set is inconsistent, then you can also show it by the paraconsistent logic. There are exceptions, but usually that holds. I remember that was one of the things that came up in the PhD of Bovenried, the man from Chile. Oh, I forgot his first name.
Andres. Andres Robin.
Yeah. It's a shame. I've read.
Miserta.
Huh?
Robin with Miserta.
Bovenried.
Miserta.
Well, he wrote his PhD in Leeds with Stephen French. And for some or other reason, Stephen got the idea that I should be the external examiner. In Britain, they have a very stupid, very strange system. So then, since I had not done this before in Britain, they appointed a member of the staff to explain to me how you have to do this. Then the funny thing was that even Stephen was even sitting in the committee where we were talking. So that was rather funny for me. Okay. Now we will see that this leads to, if you mark this, what happened here is that I have marked for reliability. You see that line 7 and 8, sorry, line 6 and 7 are marked from stage 8 on. And that's because at stage 8 you derive either P and not P or Q and not Q. So on the reliability strategy, both P and not P and Q are not Q are unreliable abnormalities. I mean, you cannot rely on their falsehood because you don't know which of them is false or true. And so then you can mark both lines 6 and 7. But if you mark them for minimum abnormality, the matter is different, and you will see what happens immediately. I had hoped that I had repeated, a number of things, but, well, maybe I just write it on the blackboard. From R, line 6 is marked, but at line 6 you have R, and at line 7 you have S, and from both of them you can derive R or S. Since this comes from line 6, then it comes on the condition that P and not P should be possible to consider P and not P as false. And on the other hand, you can derive R or S from line 7, but then of course it comes on another condition, namely Q and not Q. But if you now says one of these two is bound to be true, in the models in which this can be kept to be false, Q and not Q will be true, and in the models in which this is kept to be false, can be taken to be false, P and not P will be true. Nevertheless, in all those models you have R or S true. So this is why you get a surplus. You can never get that there in terms of, because if you since line 6 and 7 are both marked, then these two will also be marked. So on the reliability strategy, you cannot derive R or S from the premises. But on the minimum abnormality strategy, you can. And this holds in general. These are the most known strategies. It holds in general that reliability gives you a certain consequence set that extends the consequence set of the lower limit logic. But then if you move from reliability to minimum abnormality, you get a bit more of this, a bit more consequences. And you can show that it holds generally. It's always it's not always a proper set inclusion, but it's either identical or you get something more. That's the idea. So it never diminishes. By going to minimum abnormality, you never get less adaptive consequences. Of course, that's precisely now we are talking about the interesting part of the adaptive logics, namely that whenever you keep my raincoat, sorry. So the only thing that is interesting about adaptive logics is that when you use a strategy to make it dynamic, you obtain a bit more than you could obtain by the lower limit logic. Okay? So if you are happy with inconsistencies like typically Graham Priest, it's a pity he is not here because I don't like to talk about people when they are not present. But for Priest, if there is an inconsistency, well, there's no problem at all. He once got very upset because I had writing a draft of a common introduction to something or so. I talked about the problem of inconsistency. He got very upset and said, there is no problem of inconsistency. It's a feature or whatever, but not a problem. But yeah, I think it is a problem, of course, as I argued on Monday. I think it's a problem because you try to get rid of the inconsistency. So that means you consider it problematic. And well, to what extent does Grand Priest follow that? In the old days he wrote, especially when his paper on LPM, then he argues a number of times that the most inconsistencies, I say it in a restricted way, most inconsistencies are false. Or usually inconsistencies are false. And so, yeah, but why is that the case? Is that just an historical fact, or I think there's a good reason why most inconsistencies are false. Good. I think that was all I wanted to say about this thing, and I wanted to illustrate just two strategies. Actually, the minimal abnormality strategy that is more complicated, as I said, because it requires these choice sets, is simpler from the semantic point of view. Is the simplest idea, namely, you consider models and you consider their abnormal part as the contradictions the models verify. And then you look for minimal abnormal models in the literal sense, namely that whenever set theoretically the inconsistencies true in this model are a proper subset of the inconsistencies true in that model, then that model is not minimally inconsistent. Okay? So that's the minimal abnormality strategy. That's very simple and semantically speaking. Now we have seen that this is, I think, an interesting couple of remarks. We have seen that the marks may change from stage to stage. And you can indeed construct examples where at some stage line 4 will be written down and will be unmarked at the moment that it is written down. But then when you get to stage 7, line 4 will be marked. But you can construct cases where you continue and then at stage 12, line 4 is again unmarked. And this may go on ad infinitum. I mean, you can construct, and actually I did construct such cases because somebody was interested in that. Unfortunately, he was interested in it because he thought it was a way to attack adaptive logics, the idea of dynamic proof. And of course, that was mistaken. And was answered, but was not very fair that he used an example that came indirectly to him from me, through our assistant in those days, whom he had asked to collaborate in the paper. And then he had asked me do you think it is possible that there are cases where it oscillates as it were ad infinitum? So then I had constructed one. And then later, Horsten published a paper with somebody else, with Welsh, a computer scientist, I think, from Britain. They published a paper and they used the example, not mentioning either me, but probably they didn't know it came from me, but not even mentioning Guido, who had given the example to them. So I will remember Guido, I'm sure. Well, this is small history of course that is not very important.
Sorry, you said that you could unmark a line.
In the sense that, no, a line is, whether a line is marked depends on a definition. And the definition actually is different from, it's in terms of what was on the previous slide, namely, in terms of the abnormalities determined by a premise set, and this is the unreliable formula determined by the premise set, and that's the not minimal. Yeah, well, what you require for minimal abnormality strategy, you need this phi. There's no point in giving it the name. But both the U gamma and the phi of gamma are basically needed, as I said, to go from the syntax to the semantics and get to the completeness.
Okay, my question is, the idea is that as you go on with the derivation, you may find that some abnormalities are true, and so the lines that depend on them are marked,
Yes?
and they stay marked forever.
No?
No?
No.
How could you unmark a line?
Oh, well.
Oh, if you mark the line that concludes the abnormality?
No, well, suppose here is an example where I derive at line 8 a disjunction of two abnormalities, P and not P or Q and not Q. But suppose that P and not P is also derivable, then line 8 is not a minimal disjunction of abnormalities because there is a shorter one, Q and P and not P set. So then only lines that rely on P and not P will have to be marked. So in that case, line 10 will be unmarked. So
But
if
line, for example, line 7, would it remain marked?
no,
You would remove the mark.
yeah, well, according to the definition, it's a definition. Line 7 is not marked according to the definition.
Oh, at a certain stage, a line is either marked or not. Okay.
So the definition says. Now, I think I can get to where I wanted to get us, what was at the beginning of the. So now, given that there is these marks come and go, and so now it is derivable, it's not derivable according to deductive logic, so that's an unstable notion of derivability. Call that marking at a stage and derivability at a stage. The ability is important to be derivable at a stage is a kind of an ability. So if you have such an unstable notion of derivability, you also want a final stage of it, and a stable one, and that's what is called final derivability. One way to define it is to allow for infinite sequences of formulas as proofs, and then there can be some maybe transfinite point where the whole thing becomes stable. But some people don't like transfinite things. And so you can also phrase it as follows, and that's actually how it was originally phrased. If you have a proof and there is a line in it that is marked, and here you derive formula A, so the line is marked, but so A is not supposed to be derivable according to this at this stage of the proof. Now, if you have such a case where the line is marked, and you can extend the proof in such a way that the line is unmarked, then well, you change the situation, and now I give the correct definition. So if you have a proof at which A occurs on a line that was originally not marked but later gets marked, and whenever by extending the proof, no. Take a case where it is unmarked. And if by extending the proof, this is extension 1, you derive formulas that cause this line to be marked, then if second extension, if it is possible to further extend the proof in such a way that the line is again unmarked, then A is finally derivable from the premise. It sounds like a bit mysterious, but it's provably correct. And actually, the proof was already in a rather old paper. Lógica published a book in honor of Elena Raziova, who's a Polish logician who at some point died, and Eva was a good friend of her, and Eva published this book. And this paper, so that's basically the generalization of adaptive logics from the proposition level to the predicate level in the correct way. There were some papers before, but there are some obscure things in it. But there it is all done correctly, also the method. So now you can, it's interesting to describe this in terms of game theoretic, in a game theoretic way, namely, if somebody produces a proof, call this person the proponent. The proponent produces a proof in which A is unmarked. And then an opponent is able to extend the proof in such a way that the line is marked. Then the proponent should be able, for the line to be fine, for it to be finally derivable, the proponent should be able to further extend the proof in such a way that it is not marked. There are some complications in the sense that for some specific cases, you have to allow for infinite extensions. But it's possible to show there are a lot of equivalent game theoretic definitions possible. For example, you can allow them to play the same game an infinite number of times. That doesn't make a difference. If you require it once, if you say, if there is a proof in which it's unmarked, and whenever somebody is able to extend the proof in such a way that the line is marked, then the proponent should again be able to further extend in such a way that it is unmarked again. So unmarked does not refer to the fact that the user of the logic is doing something, like adding a check or not adding a check. Just refers to the definition. It's unmarked is something stable, just like marked. Okay, meaning it's not going to definition marked. Okay. So that paper on this game theoretic thing was published in a fastschrift for Rama from Lille. Some people know him, I think he has. Walter knew him at least.
He spent some time here in Campinas. He spent some time here in Campinas. I did a course with him here. He lived here.
Shahid is a man of Indian descendants, but he ended up in the end, he was a while with Kuno Lorenz in Saarbrücken, I think. That's when I first met him, and then later he got a position in Lille, which is in the north of France.
I think he's Argentinian. He was born actually.
Yeah, but he's of Indian descendants. I mean, his forefathers were Indian, but I think, I remember now. He's an Argentinian
His
citizen.
mother was German. His mother.
I know him since I was a child. He's in Bahia Blanca.
Yeah.
His father was rector of our university.
Yeah, he had a rather heavy period, and a period in his life was very difficult because his wife died of cancer at a certain moment, and he was extremely worried by it. the whole process, of course. This is a number of years ago. So, but yeah, he is mainly interested in game theoretic approaches and yeah. Would like me to stop?
Yeah.
Okay, well, you are the boss. If you manage to find somebody that I can make an appointment with for tomorrow, that I find the building a bit more easily than
Okay.
today. Because today I had even to enter a non-university building and ask, that's all I remember, the Ciclo Básico. And the man fortunately knew what it was and where it was. Okay, so there are 2 more days to go. Correct? You are Wednesday, there's still Thursday and Friday. So, yeah. Good, we'll get there.